There are storms on Earth that seem almost impossible. Storms powerful enough to tear roofs from buildings, uproot ancient trees, and reshape entire coastlines in a matter of hours. The strongest winds ever directly measured on our world reached astonishing speeds during Tropical Cyclone Olivia in 1996. On a remote island off the coast of Australia, instruments recorded a gust of 254 miles per hour. For us, that number feels almost unreal. At those speeds, the air itself becomes a weapon. Ordinary objects transform into projectiles. Structures collapse. Landscapes change. Human beings can do little more than seek shelter and wait for nature's fury to pass. And yet, in the vastness of the solar system, Earth's most violent storms barely qualify as a warm-up. Far beyond our world, beyond the orbit of Mars, and across hundreds of millions of kilometers of empty space, hangs a planet where storms have raged continuously for centuries. Not days, not weeks, not even decades. Centuries. Imagine standing on a world where a hurricane began before your great-great-great-grandparents were born and continues spinning today. That world is Jupiter. From Earth, Jupiter appears calm and beautiful. Through a telescope, its creamy bands stretch across its enormous disk, like brushstrokes painted by some cosmic artist. But hidden within those colorful clouds is one of the most extreme weather systems known to science. A storm so large that our entire planet could disappear inside it. A storm known as the Great Red Spot. For generations, astronomers stared at that strange crimson oval and wondered what exactly they were looking at. At first, it appeared almost decorative, a simple mark on Jupiter's face. But as telescopes improved and spacecraft finally approached the giant planet, the truth emerged. The Great Red Spot is not a stain. It is not a crater. It is not a mountain. It is a hurricane-like vortex of unimaginable size. At its widest, the storm stretched nearly 3 times wider than Earth itself. Winds race around its perimeter at speeds reaching over 400 miles per hour. Entire continents could fit comfortably within its swirling boundaries. If such a storm somehow appeared on Earth, civilization would not survive it. Yet on Jupiter, it is merely one feature among many. The deeper scientists looked, the stranger the story became. For centuries, nobody knew how deep the Great Red Spot extended beneath Jupiter's clouds. The visible portion was only the top layer of an enormous atmospheric machine. Then NASA's Juno spacecraft arrived and began collecting data from closer than any mission before it. What it revealed was astonishing. The storm does not merely skim the cloud tops. It plunges hundreds of kilometers into Jupiter's atmosphere, deeper than Earth's deepest oceans, deeper than Mount Everest is tall, a gigantic atmospheric engine reaching far beneath the visible surface of the planet. And perhaps even that measurement is only part of the story. The truth is that Jupiter remains mysterious. Unlike Earth, it has no solid surface waiting beneath the clouds. There is no coastline, no mountain range, no bedrock. The deeper you descend, the atmosphere simply becomes denser and denser until gases begin behaving like liquids. The Great Red Spot spins within this endless ocean of atmosphere. There is nothing beneath it to slow it down, nothing to weaken it, nothing to stop it. On Earth, hurricanes eventually encounter land. Friction robs them of energy. Mountains disrupt airflow. Continents break their structure apart. Jupiter offers no such resistance. Its storms can continue almost indefinitely. And that may explain why the Great Red Spot has survived for hundreds of years. But size is only part of what makes this storm extraordinary. Temperature reveals an even stranger reality. The upper cloud layers surrounding Jupiter are unimaginably cold. Temperatures can plunge to minus 234 degrees Fahrenheit. Yet directly above the Great Red Spot, scientists discovered something unexpected: extreme heat, temperatures exceeding 2,400 degrees Fahrenheit, hotter than molten lava. How can a freezing atmosphere contain regions hotter than volcanic rock? The answer appears to lie in the storm itself. As powerful winds churn through Jupiter's atmosphere, they generate enormous waves of energy: sound waves, gravity waves, atmospheric disturbances so powerful that they travel upward through the planet's skies. These waves eventually break and release energy, heating the upper atmosphere to extraordinary temperatures. In a sense, the storm is creating its own furnace, a weather system so powerful that it changes the thermal structure of an entire planet. And yet, despite centuries of observation, we still don't fully understand it. Scientists continue debating why the storm is red. Some theories suggest complex chemical reactions driven by ultraviolet sunlight. Others point toward compounds rising from deeper atmospheric layers. Certain chemicals may become altered by radiation and transform into the distinctive reddish-orange hue we see from Earth. Nobody knows for certain. The Great Red Spot remains one of the solar system's most famous mysteries. But perhaps the strangest part of all is that the storm may be dying. For decades, astronomers have watched it slowly shrink. Measurements show that it is significantly smaller than it was in the 19th century. In recent years, chunks of reddish material have appeared to peel away from its outer edges before disappearing into Jupiter's atmosphere. The storm is becoming smaller, taller, and more intensely colored, almost as though it is changing into something new, or perhaps approaching its final chapter. One day, maybe decades from now, future astronomers may look toward Jupiter and discover that the Great Red Spot has vanished, a storm that survived empires, a storm that outlived generations, a storm older than modern science itself. Gone. And yet, even if the Great Red Spot eventually disappears, Jupiter will remain a world of storms, because the deeper we venture into the solar system, the more we discover that weather is not merely an earthly phenomenon. It is a universal force, a force that shapes planets, sculpts atmospheres, and reveals the hidden physics of worlds far beyond our own. And as we continue our journey outward, we are about to encounter storms even stranger than Jupiter's legendary red giant. Storms that circle entire planets. Storms with 6 sides. Storms where winds move faster than sound itself. And that is where our story continues. If the Great Red Spot vanished tomorrow, Jupiter would still remain the undisputed king of weather in our solar system. The famous Crimson Vortex may dominate photographs and documentaries, but it is only one storm among countless others raging across the giant planet. Jupiter's atmosphere is a constantly shifting ocean of turbulence, where powerful jet streams race around the globe, colliding, twisting, and spawning vortices large enough to swallow entire worlds. Some of these storms appear briefly before fading away. Others survive for years. A few have become permanent landmarks. One of the most fascinating is known as the Little Red Spot. The name makes it sound insignificant, almost cute, compared to its gigantic sibling. In reality, the Little Red Spot is itself roughly the size of Earth. Winds inside this smaller anticyclone have been measured approaching 400 miles per hour. On our planet, such a storm would be remembered as the greatest natural disaster in human history. On Jupiter, it barely earns a nickname. The giant planet exists in a perpetual state of atmospheric unrest. Heat rises from deep below, while sunlight warms the upper layers. The result is an endless struggle between energy sources, creating patterns and storms unlike anything Earth could ever produce. Yet, strangely enough, Jupiter is not even the most extreme world when it comes to wind speed. Farther from the Sun lies Neptune, a blue giant wrapped in mystery. Neptune receives roughly 1,000th of the sunlight that Earth does. Logic suggests it should be calm. Cold worlds should be quiet worlds. At least that is what scientists once believed. Instead, Neptune hosts some of the fastest winds ever observed anywhere in the solar system. Massive dark storms appear within its atmosphere like bruises emerging from beneath the clouds. Around these giant vortices, winds can exceed 1,300 miles per hour. To put that into perspective, a commercial airliner cruises at around 550 miles per hour. Neptune's winds move more than twice as fast. The puzzle becomes even more confusing when scientists realize that sunlight alone cannot explain this violence. Neptune somehow generates additional heat from its interior. Something hidden deep within the planet continues feeding its atmosphere with energy. The exact mechanism remains uncertain. Whatever is happening inside Neptune, it powers weather systems capable of outrunning almost anything humanity has ever built. Meanwhile, Saturn offers an entirely different form of atmospheric madness. At first glance, Saturn appears peaceful. Its rings create an image of elegance and serenity, unmatched anywhere else in the solar system. But beneath that beauty lies one of the strangest storms ever discovered. Hovering over Saturn's north pole is a gigantic vortex surrounded by a perfect hexagon. Not an approximate hexagon, not something vaguely six-sided. A remarkably precise six-sided structure stretching across thousands of miles. Imagine flying above Earth and discovering that a hurricane had somehow organized itself into a giant geometric shape visible from space. Scientists were stunned when they first observed Saturn's hexagon. Decades later, it remains one of planetary science's greatest mysteries. The storm stays anchored to the North Pole rather than drifting like hurricanes on Earth. It rotates continuously, maintaining its bizarre shape year after year. The eye at its center is enormous, far larger than any terrestrial hurricane. Winds race around its boundaries at hundreds of miles per hour. Yet despite countless observations, researchers still debate exactly why the hexagon exists at all. Saturn also experiences another extraordinary phenomenon known as the Great White Spot. Unlike the permanent hexagon, this storm appears roughly every 30 years. It begins as a relatively small disturbance before rapidly expanding across the planet. Eventually, it stretches so far that it wraps around Saturn like a belt. At its peak, lightning flashes inside the storm more than 10 times every second. Imagine standing beneath a thunderstorm where lightning never stops. One flash after another, continuously illuminating the clouds. The energy involved is staggering. Yet even here, scientists are unsure what ultimately powers the system. Some evidence points toward solar heating. Other observations suggest internal heat sources hidden beneath Saturn's cloud layers. The truth may involve a combination of both. Then there is Venus, often called Earth's twin because of its similar size. In reality, Venus is one of the most hostile worlds known. Thick clouds of sulfuric acid surround the planet. Surface temperatures are hot enough to melt lead. Atmospheric pressure would crush an unprotected human instantly. Yet even within this hellish environment, weather creates astonishing structures. Near Venus's south pole lies a giant vortex, roughly the size of Europe. The atmosphere itself moves around the planet 60 times faster than the planet rotates beneath it. Imagine standing on a world where the air races around the globe while the planet struggles to keep up. Venus demonstrates that weather is not simply something that happens above a planet. In many cases, weather becomes the dominant force shaping the entire world. Mars offers a completely different lesson. Unlike the giant planets, Mars has a thin atmosphere. Yet, despite possessing less than 1% of Earth's atmospheric density, it can produce dust storms so enormous that they engulf the entire planet. These storms begin innocently enough. Dust rises into the air and absorbs sunlight. The atmosphere warms. Warm air creates stronger winds. Stronger winds lift more dust. More dust traps additional heat. A self-reinforcing cycle develops. Eventually, the entire planet can disappear beneath a blanket of airborne particles. For months at a time, Mars becomes a world hidden behind its own weather. Spacecraft on the surface watch sunlight fade. Horizons vanish. The planet transforms into a global storm system, visible from millions of miles away. The deeper scientists explore the solar system, the more they realize that weather is not a local phenomenon. It is a universal language spoken by planets. Different atmospheres produce different accents, but the same underlying principles appear everywhere. Heat seeks balance. Energy flows from one region to another. Gases rise and fall. Pressure differences generate motion. Given enough time, enough energy, and enough space, nature creates storms. What makes these alien storms so fascinating is not merely their size. It is what they reveal about the worlds that host them. A storm is a messenger, carrying information from regions we cannot directly observe. The Great Red Spot tells us about Jupiter's deep atmosphere. Neptune's dark vortices hint at hidden internal heat sources. Saturn's hexagon reveals atmospheric physics we still struggle to understand. Even Mars's dust storms preserve clues about a warmer and wetter past. In a sense, every storm is a conversation between a planet's present and its history. And nowhere is that conversation more dramatic than on Mars, where weather may hold the key to understanding how an entire world transformed from a potentially habitable planet into the cold desert we see today. Because the next chapter of our journey is not about storms that exist now, it is about a world that lost almost everything it once had. Today, Mars feels ancient. Not ancient in the way a mountain feels ancient or an abandoned city feels ancient. Mars feels ancient in the way a skeleton feels ancient. It is a world that seems to be missing something essential. A planet that looks as though life packed its belongings billions of years ago and quietly left. When we look at Mars through telescopes or from orbiting spacecraft, we see endless deserts, rust-colored plains, frozen poles, and gigantic volcanoes standing silent beneath a pale sky. Temperatures frequently plunge far below anything most places on Earth ever experience. Liquid water cannot survive for long on the surface. The atmosphere is so thin that a person standing there without protection would lose consciousness within seconds. Yet the deeper scientists investigate Mars, the stranger the story becomes, because everything about the planet suggests it was once completely different. Billions of years ago, Mars may have looked surprisingly familiar. Rivers flowed across its surface. Vast lakes occupied enormous basins. Oceans may have covered significant portions of the northern hemisphere. Rain likely fell from clouds. Snow may have accumulated on mountain slopes. Valleys carved into the landscape reveal unmistakable signs of moving water. Ancient shorelines seem frozen into the terrain. Everywhere scientists look, they find evidence that Mars once possessed something it has now lost: a thicker atmosphere, and with it, a completely different climate. The question is not whether Mars changed. The question is how an entire planet can lose an atmosphere thick enough to support rivers and lakes. The answer begins deep beneath the Martian surface. Like Earth, ancient Mars possessed a molten interior. As liquid metals moved inside the planet's core, they generated a magnetic field. This invisible shield extended far into space, surrounding the planet and protecting it from one of the greatest dangers in the solar system, the solar wind. At first glance, the solar wind sounds harmless. Wind is something we experience every day on Earth. But the solar wind is not air. It is a continuous stream of charged particles blasting outward from the sun at incredible speeds. Every second, our star throws billions upon billions of particles into space. Earth survives this assault because of its magnetic field. The invisible shield deflects most incoming particles, forcing them around the planet. Occasionally, some particles slip through near the poles, producing beautiful auroras. But for the most part, Earth's atmosphere remains protected. Mars was not so fortunate. At some point in its history, the planet's interior cooled enough for its magnetic field to weaken and eventually disappear. Once that shield vanished, the atmosphere stood exposed. Imagine removing the roof from a house during a hurricane. Now imagine doing that continuously for hundreds of millions of years. Particle by particle, molecule by molecule, the solar wind began stripping away Mars's atmosphere. The process was slow by human standards, but astonishingly fast on geological timescales. Over a few 100 million years, much of the atmosphere simply escaped into space. As the atmosphere thinned, temperatures dropped. As temperatures dropped, water began freezing. As water froze, the climate became even colder. A vicious cycle unfolded. The once habitable world gradually transformed into a frozen desert. What remains today is merely a shadow of what Mars may once have been. Yet even in its diminished state, Mars continues to surprise scientists. One of the most dramatic examples comes in the form of its global dust storms. At first, this seems impossible. Mars has an atmosphere less than 1% as dense as Earth's. Intuitively, such a thin atmosphere should be incapable of generating powerful weather. Yet every few years, dust storms erupt and spread across the planet until they cover entire hemispheres. Some become so large that Mars itself nearly disappears from view. The mechanism behind these storms is elegant and terrifying. Dust particles absorb sunlight and warm the atmosphere around them. Warm air begins moving toward cooler regions. Winds strengthen. Stronger winds lift additional dust. More dust means more heating. More heating means stronger winds. The cycle feeds itself. What begins as a local disturbance can eventually engulf an entire world. For robotic explorers on the Martian surface, these storms are more than scientific curiosities. They can become life-threatening events. Solar-powered rovers may lose access to sunlight for weeks. Temperatures fluctuate dramatically. Visibility collapses. The sky turns into a swirling wall of rust-colored darkness. And yet these storms are only part of the story. Mars also preserves records of climate changes, spanning hundreds of millions of years. Hidden within its glaciers are clues to ancient ice ages that came and went long before complex life emerged on Earth. Scientists studying orbital imagery discovered enormous debris-covered glaciers stretching across parts of the planet. These formations act like frozen archives. Every layer tells a story. Every band of rock marks a different chapter in Martian history. Researchers examining these patterns concluded that Mars likely experienced numerous separate ice ages over the past several 100 million years. Instead of one long frozen period, the planet appears to have cycled repeatedly between different climatic states. In other words, Mars has a climate history every bit as complex as Earth's, perhaps even more complex. These glaciers fascinate scientists because they may preserve ancient material trapped for unimaginable lengths of time. Tiny pockets of gas, fragments of rock, organic compounds, maybe even evidence of microbial life if such life ever existed. Unlike Earth, where active geology constantly recycles the surface, Mars often preserves its history in remarkable detail. Ancient environments remain frozen in place, like snapshots from another era. And then there are the scars. Across the Martian landscape lie gigantic channels and floodplains hinting at catastrophes almost beyond comprehension. Some researchers believe enormous impacts melted vast quantities of ice, unleashing floods of staggering scale. Water surged across the surface, carving valleys and depositing sediments that remain visible billions of years later. Certain wave-like formations rise more than 30 feet high and stretch hundreds of feet apart. They resemble the aftermath of colossal tsunamis frozen in stone. It is difficult to imagine such scenes when looking at modern Mars. Today, the planet appears quiet, still, almost lifeless. But beneath that silence lies evidence of a violent and dynamic past. A world that once possessed rivers, lakes, glaciers, storms, floods, and perhaps all the ingredients necessary for life. And that realization leads to an unsettling question. If Mars could lose an atmosphere, lose its oceans, and lose the conditions that once made it potentially habitable, could something similar happen elsewhere? Because as we continue our journey through the solar system, we are about to encounter worlds where weather becomes even more violent, where lightning dwarfs anything seen on Earth, and where entire planets seem determined to remind us just how fragile a habitable world truly is. If Mars tells the story of a world that slowly died, Venus tells the story of a world that became trapped. At first glance, Venus should have been one of the most Earth-like planets in the solar system. It is similar in size, similar in mass, similar in composition. If you were designing a second Earth, Venus would seem like an obvious candidate. Yet somehow, everything went wrong. Today, Venus is the hottest planet orbiting the Sun, not Mercury, despite being closer to our star. Venus. Its thick atmosphere acts like a gigantic thermal blanket, trapping heat so efficiently that surface temperatures climb above 860 degrees Fahrenheit. Hot enough to melt lead. Hot enough to destroy most spacecraft within hours. Hot enough to transform an entire world into something resembling a planetary pressure cooker. Standing on the surface of Venus would feel less like visiting another planet and more like descending into a giant industrial furnace. The atmosphere presses down with crushing force, equivalent to being nearly a kilometer underwater on Earth. Above you hangs a sky filled with clouds of sulfuric acid. Rain forms within these clouds, but the droplets never reach the ground. The atmosphere is so hot that they evaporate before completing their descent. It rains acid, and even that rain cannot survive. Yet despite these hellish conditions, Venus possesses one of the solar system's most fascinating weather systems. Near its south pole spins an enormous atmospheric vortex, roughly the size of Europe. This storm has likely existed for an extremely long time, perhaps centuries or even longer. The atmosphere surrounding it behaves in ways that continue to puzzle scientists. One of the strangest features of Venus is that its atmosphere moves dramatically faster than the planet itself rotates. A single day on Venus lasts longer than an entire Venusian year. The planet rotates so slowly that if you stood on its surface, you could watch the sun crawl across the sky at a pace almost impossible to imagine. The atmosphere, however, refuses to wait. Powerful winds race around the globe at speeds reaching hundreds of miles per hour, completing a journey around the planet far faster than the surface beneath them. Imagine clouds circling Earth every few days while the planet itself barely moved. That is essentially what happens on Venus. Scientists call this phenomenon atmospheric superrotation, and despite decades of study, many details remain unclear. Somewhere within Venus's dense atmosphere lies a mechanism capable of transferring enormous amounts of energy into motion. The planet remains one of the greatest unsolved weather mysteries in our cosmic neighborhood. Yet Venus is not alone. Far beyond Saturn's magnificent rings lies Uranus, a world so unusual that it appears to have been knocked over. Most planets spin roughly upright relative to their orbit around the Sun. Uranus does not. It rotates almost completely on its side, as though some giant hand tipped it over billions of years ago. Scientists suspect that may be exactly what happened. A massive collision early in the solar system's history could have struck Uranus with enough force to permanently alter its orientation. The consequences remain visible today. Seasons on Uranus are unlike anything experienced elsewhere. Portions of the planet spend decades facing the sun before spending decades facing away. A season on Uranus lasts around 42 Earth years. Entire generations could be born, grow old, and die during a single Uranian summer. The planet itself appears calm from a distance, but closer observations reveal surprisingly dynamic weather. Clouds form and disappear. Powerful storms emerge unexpectedly. Atmospheric structures evolve over time. Even in the dim outer reaches of the solar system, weather continues to shape planetary environments. Then comes Neptune. The farther scientists travel from the sun, the stranger things become. Neptune receives only a tiny fraction of the sunlight Earth enjoys. Logic suggests it should be cold, quiet, and inactive. Instead, Neptune seems almost angry. The planet hosts gigantic dark storms, resembling cosmic bruises. Winds exceed 1,300 miles per hour, making them the fastest planetary winds ever observed. Bright methane clouds race through the atmosphere. Storm systems appear and vanish with little warning. Perhaps most mysterious of all, Neptune radiates more energy than it receives from the sun. Something inside the planet generates additional heat. That heat powers weather. That weather powers storms. And those storms challenge our understanding of how planetary atmospheres should behave. The deeper we explore, the more nature seems determined to remind us that planets are not simple objects. They are living systems, not alive in the biological sense, but active, dynamic, evolving. Each world tells a different story, and nowhere is this more obvious than on Saturn. When NASA's Cassini spacecraft arrived at Saturn, it revealed storms unlike anything scientists expected. Lightning bolts erupted within gigantic cloud systems. Some discharges were so powerful that instruments could detect them from extraordinary distances. On Earth, lightning is impressive. On Saturn, lightning becomes monstrous. Individual bolts can release thousands of times more energy than typical terrestrial strikes. Cassini even recorded the sounds generated by these storms. Hidden within radio emissions were signatures of enormous electrical discharges ripping through Saturn's atmosphere. For the first time, humanity could effectively listen to alien thunderstorms occurring hundreds of millions of miles away. The recordings transformed Saturn from a distant object into a real place, a world with weather, a world with storms, a world with thunder. Then there is the hexagon. Even now, decades after its discovery, Saturn's six-sided storm remains one of the most bizarre atmospheric structures ever observed. It circles the North Pole like an immense geometric machine built by nature itself. The vortex extends deep into the atmosphere and reaches hundreds of miles above surrounding cloud layers. Nothing quite like it exists on Earth. Perhaps most fascinating is how stable it remains. Earth's storms drift. They weaken. They collapse. The hexagon persists, year after year, decade after decade, as though Saturn has carved a permanent weather pattern into its own atmosphere. Scientists have recreated similar structures in laboratory experiments using rotating fluids, but no explanation fully captures the complexity of the real phenomenon. Nature, once again, remains one step ahead. As remarkable as all these planetary storms may be, they pale in comparison to the largest weather engine in our solar system. Because there is one object whose eruptions influence every planet, one object whose storms can disrupt satellites, damage power grids, and alter conditions across millions of miles of space. One object capable of affecting Earth without ever leaving its place at the center of the solar system, the Sun itself. And as we are about to discover, our star is not the calm, glowing sphere it appears to be from Earth. Beneath its bright surface lies a realm of magnetic violence powerful enough to reshape entire worlds. Every second of every day, the Sun performs an act so violent that if it happened anywhere near Earth, civilization would instantly cease to exist. And yet, from our perspective, it looks peaceful. A glowing golden disk hanging in the sky, a familiar presence that rises every morning and disappears every evening. Most people rarely think about it beyond checking the weather forecast or enjoying a sunny afternoon. But the Sun is not calm. The Sun is a gigantic nuclear reactor containing 99.8% of all the mass in the solar system. Deep within its core, temperatures reach nearly 27 million degrees Fahrenheit. Every second, hundreds of millions of tons of hydrogen are converted into helium. The process releases an unimaginable amount of energy. That energy travels outward through the star before eventually escaping into space. Some of it reaches Earth. Without it, life would never have existed. But the same star that makes life possible also possesses the power to destroy much of what humanity has built. Because the Sun is not simply generating light, it is generating weather. Not weather in the familiar sense of rain, clouds, or wind. Instead, the Sun creates space weather, a phenomenon that extends across billions of miles and affects every planet in its reach. The source of this weather lies within the Sun's magnetic field. The star is not solid. It is composed of plasma, a superheated state of matter in which atoms are stripped apart into charged particles. This plasma constantly moves. Different regions rotate at different speeds. Some layers churn like boiling water. Others twist and stretch magnetic field lines until they become tangled knots of stored energy. Eventually, those knots snap. And when they do, the results are extraordinary. Gigantic explosions known as solar flares erupt from the Sun's surface. In mere minutes, a single flare can release as much energy as billions of nuclear bombs. Vast clouds of charged particles are hurled into space. Radiation races outward at the speed of light. For planets caught in the path of these eruptions, the consequences can be significant. Fortunately, Earth possesses several layers of protection. Our atmosphere absorbs much of the incoming radiation. Our magnetic field deflects countless charged particles. Together, They create a shield that has protected life for billions of years. Yet even with those defenses, powerful solar storms can still affect us. Throughout history, the sun has occasionally reminded humanity that we remain connected to events occurring 93 million miles away. One of the most famous examples occurred in 1859. At the time, humanity's most advanced communication network consisted of telegraph systems stretching across continents. Operators suddenly began reporting strange behavior. Sparks jumped from equipment. Some telegraph lines continued functioning even after power supplies were disconnected. Auroras appeared far beyond their usual locations, illuminating skies across much of the world. The event became known as the Carrington Event. It remains the most powerful solar storm ever recorded. If a similar eruption struck modern civilization today, the consequences would extend far beyond malfunctioning telegraphs. Satellites could be damaged, power grids could fail, navigation systems could become unreliable, communication networks might experience major disruptions. The technology that defines modern civilization is surprisingly vulnerable to conditions in space, and the sun occasionally reminds us of that fact. Even relatively recent solar storms have caused significant problems. In 1989, a powerful geomagnetic storm knocked out electricity across large portions of Quebec, leaving millions without power for hours. All of this occurred because of activity on a star millions of times larger than Earth. Yet the sun's storms are not merely destructive. They are also beautiful. When charged particles from solar eruptions interact with Earth's magnetic field, they become trapped and guided toward the polar regions. There, they collide with atoms high in the atmosphere. The result is one of nature's most spectacular displays: auroras, curtains of green, red, and purple light dancing across the sky. For thousands of years, people looked at these displays with wonder. Ancient cultures created myths to explain them. Warriors saw celestial battles. Others imagined spirits crossing the heavens. Today, we understand the science behind auroras, yet understanding has not diminished their beauty. If anything, it has enhanced it. Knowing that these lights originate from interactions between our planet and a star 93 million miles away makes them even more remarkable. The sun's influence extends far beyond Earth. Jupiter experiences auroras too. So does Saturn. In fact, all 4 giant planets possess their own versions of these glowing displays. Some are visible only in ultraviolet wavelengths, invisible to human eyes. Others are powered not only by the solar wind, but also by particles originating from volcanic moons and planetary magnetospheres. Entire worlds glow because of interactions with their parent star. The solar system is far more interconnected than it appears, and nowhere is that connection more dramatic than on Jupiter. Because while solar storms may occasionally affect Earth, Jupiter exists in a completely different category. Its immense magnetic field is the largest planetary structure in the solar system. If human eyes could see magnetic fields, Jupiter's magnetosphere would appear larger than the moon in our sky despite being hundreds of millions of miles away. It dominates an enormous region of space. It traps particles, channels energy, shapes radiation belts, and creates some of the most extreme environments known around any planet. In many ways, Jupiter behaves like a miniature solar system within the solar system. Its influence extends to dozens of moons, vast radiation zones, and countless smaller objects passing through its gravitational reach. Which raises an intriguing question. What exactly is Jupiter? Is it merely a planet? Or is it something halfway between a planet and a star? Because the deeper scientists investigate the giant world, the more they realize that Jupiter occupies a strange category all its own: a failed star, a planetary giant that came surprisingly close to becoming something much greater. And in the next chapter, we are going to explore what would happen if Jupiter crossed that final threshold and awakened into a second sun. Jupiter is often called a failed star. At first, that sounds like an insult, a cosmic near miss, a giant world that almost achieved greatness but fell short at the last moment. Yet the reality is far more fascinating. Jupiter is not merely a large planet. It occupies a strange middle ground between worlds and stars, existing right at the edge of what nature allows. When you look at Jupiter through a telescope, it is easy to underestimate just how enormous it truly is. The planet is more than 11 times wider than Earth. Over 300 Earths could be packed into its mass. In fact, Jupiter contains more than twice the mass of all the other planets in the solar system combined. If every planet were placed on a giant cosmic scale, Jupiter would dominate the measurement. And yet, despite its immense size, it is still nowhere near massive enough to become a true star. Stars are born when gravity becomes overwhelming. As enormous clouds of hydrogen collapse under their own weight, temperatures and pressures rise dramatically. Eventually, the core becomes so hot and dense that hydrogen atoms begin fusing together. At that moment, a star ignites. A self-sustaining nuclear furnace is born. The Sun achieved this state because it contains about 1,000 times Jupiter's mass. That number is almost impossible to visualize. Imagine stacking one Jupiter on top of another, then another, then another. You would need 1,000 of them before reaching the mass of our Sun. Yet, there is an interesting twist. Jupiter does not need to become as massive as the Sun to begin behaving like a star. There exists a category of objects known as brown dwarfs. Brown dwarfs occupy the strange territory between planets and stars. They are often called failed stars as well, but unlike Jupiter, they briefly ignite limited fusion reactions before fading into relative darkness. To transform Jupiter into a brown dwarf, you would need roughly 80 times its current mass, still an enormous increase, but far less than what would be required to create a true sun-like star. If somehow 80 additional Jupiters appeared and merged with the planet, the solar system would change forever. Temperatures within Jupiter's core would soar. Pressure would become unimaginable. Fusion reactions would begin. A second stellar object would emerge, not bright enough to rival the Sun, but bright enough to fundamentally alter life throughout the solar system. Earth's nights would never become truly dark again. A dim reddish star would share the sky with the Sun. Planetary orbits would slowly shift under the influence of the new gravitational balance. Temperatures throughout the solar system would change. Entire climates could evolve in response. Human civilization would live beneath a sky unlike any experienced by our ancestors. Fortunately, Jupiter lacks the mass required for such a transformation, but that has not stopped scientists from wondering about more extreme possibilities. What if Jupiter exploded? At first glance, the idea sounds ridiculous. After all, Jupiter consists largely of hydrogen and methane. Both are combustible substances under the right conditions. People often imagine Jupiter as a giant ball of fuel waiting for a spark. If someone somehow carried a match into Jupiter's atmosphere, would the planet ignite like an enormous gas cloud? The answer is surprisingly simple. No. Fire requires 3 ingredients: fuel, heat, and oxygen. Jupiter has plenty of fuel. Hydrogen dominates its atmosphere. Methane is present as well. There is no shortage of combustible material. The problem is oxygen. There simply is not enough. Without oxygen, combustion cannot sustain itself. A match brought into Jupiter's atmosphere would fail just as surely as a candle sealed beneath a glass jar. Even enormous impacts fail to ignite the planet. And Jupiter gets hit all the time. Its immense gravity acts like a cosmic vacuum cleaner, attracting asteroids and comets from across the solar system. Some impacts release energy equivalent to billions of nuclear bombs, yet Jupiter never catches fire. The most famous example occurred in 1994. Astronomers watched in fascination as comet Shoemaker-Levy 9 approached the giant planet. Long before impact, Jupiter's gravity tore the comet apart into more than 20 separate fragments. Instead of colliding as a single object, the fragments lined up like train cars racing toward their destination. Then the bombardment began. One after another, the fragments slammed into Jupiter's atmosphere at astonishing speeds. Fireballs erupted, shock waves expanded, gigantic plumes shot thousands of miles above the cloud tops. Some scars left behind were nearly the size of Earth itself. For the first time in human history, scientists witnessed a planetary collision of truly cosmic proportions. And still Jupiter survived without difficulty. Within weeks, many of the visible scars began fading. The atmosphere absorbed the damage. The giant planet simply moved on. That event revealed something important. Jupiter is far more resilient than it appears. To actually destroy the planet would require energies beyond anything humanity can currently imagine producing. Even the largest nuclear arsenal ever built would be insignificant compared to the forces shaping Jupiter every day. Yet the thought experiment remains fascinating. Suppose some impossibly advanced civilization managed to detonate Jupiter. Suppose they somehow triggered a reaction powerful enough to tear the giant apart. The consequences would not stop at Jupiter. Earth would suffer as well. Jupiter's gravity plays a critical role in stabilizing parts of the solar system. Remove the giant planet, and countless orbital relationships would change. Asteroids that once followed stable paths might become unpredictable. Some could be redirected toward the inner planets. The solar system would become a more dangerous place, not overnight, but gradually, over millions of years. There is another reason Jupiter matters. It acts as both protector and troublemaker. For decades, scientists viewed Jupiter primarily as Earth's guardian. Its gravity captures comets and asteroids that might otherwise threaten our planet. There is truth to that idea. The Shoemaker-Levy collision itself demonstrated Jupiter's role as a celestial shield. Yet newer research reveals a more complicated picture. Sometimes Jupiter protects Earth. Sometimes it redirects objects toward Earth. Its gravity does not choose sides. It simply follows the laws of physics. In some scenarios, Jupiter prevents impacts. In others, it creates them. And that realization leads us into one of the most dramatic stories in planetary history, because there is growing evidence that Jupiter may have influenced events that change the course of life itself. Events involving giant impacts, mass extinctions, the rise of mammals, and perhaps even the reason humans exist today. To understand that story, we need to travel back tens of millions of years and examine how a giant planet billions of miles away may have helped shape the fate of Earth. 66 million years ago, the world ended. Not for the planet itself. Earth survived. The oceans remained. The continents endured. Mountains still stood where they had stood before. But for the creatures that ruled the planet, everything changed. The sky turned dark. Forests burned. Shock waves raced around the globe. Tsunamis crossed entire oceans. And within a relatively short period of geological time, nearly 3/4 of all species disappeared. Among the victims were the dinosaurs, the dominant animals of their age. For decades, scientists have investigated the object responsible for this catastrophe. The impact site lies beneath the Yucatan Peninsula in modern-day Mexico. Hidden beneath layers of rock is the enormous Chicxulub crater, one of the largest impact scars on Earth. The object that created it was roughly 6 to 10 miles wide. That may not sound particularly large compared to planets or moons, but size alone is misleading. An object moving through space carries tremendous kinetic energy. When something that large strikes a planet at cosmic speeds, the energy release becomes almost unimaginable. The collision unleashed more power than billions of nuclear weapons. Entire ecosystems vanished. Global temperatures fluctuated dramatically. Dust and debris filled the atmosphere, blocking sunlight for months or even years. Photosynthesis collapsed. Food chains unraveled. The age of dinosaurs came to an end. And from the ashes of that disaster, mammals began their rise. Eventually, after millions of years of evolution, one particular mammal species would begin asking questions about the stars, us, which leads to an unsettling possibility. What if the chain of events that eventually led to humanity began not on Earth, but with Jupiter? Scientists have debated this question for years. One theory suggests the Chicxulub impactor may not have been an asteroid at all. Instead, it may have been a comet originating from the distant outskirts of the solar system. Far beyond Neptune lies a vast reservoir of icy objects known as the Oort cloud. It stretches almost unimaginably far into space, forming a gigantic shell around the solar system. Occasionally, one of these icy wanderers becomes disturbed. A passing star, a gravitational interaction, a subtle nudge accumulated over millions of years. Whatever the cause, the comet begins falling inward toward the sun, and eventually it enters the domain of Jupiter. This is where things become interesting. Jupiter's gravity is so powerful that it can dramatically alter the paths of incoming objects. Sometimes it captures them. Sometimes it ejects them entirely from the solar system. Sometimes it redirects them onto new trajectories. In effect, Jupiter acts like a giant gravitational slingshot. An incoming comet may arrive with one orbit and leave with a completely different one. That means Jupiter is not simply a shield. It is also a cosmic traffic controller, and traffic controllers occasionally send things in unfortunate directions. Researchers using computer simulations discovered that Jupiter is equally capable of protecting Earth and endangering it. In some scenarios, its gravity intercepts dangerous objects before they reach the inner solar system. In others, it redirects them toward planets that would otherwise have remained safe. Jupiter is neither hero nor villain. It is simply enormous, and enormous things influence everything around them. One fascinating example occurred in 1770. An object known as Lexell's comet passed remarkably close to Earth. By astronomical standards, the encounter was alarmingly intimate. The comet came within about 1.4 million miles of our planet. That sounds far away. In everyday life, it certainly is. But on cosmic scales, it was practically a near miss. The comet's journey had been dramatically altered by an earlier encounter with Jupiter. The giant planet had effectively grabbed the object, reshaped its orbit, and flung it inward toward Earth. Fortunately, the comet missed. Had circumstances been slightly different, history might have unfolded very differently. Yet blaming Jupiter would be unfair, because there is another side to the story. Many scientists believe Jupiter may have helped make life possible in the first place. Early Earth was not born with oceans. Water had to come from somewhere. One leading hypothesis suggests that icy asteroids and comets delivered much of Earth's water during the chaotic early history of the Itzazuruk solar system. These impacts may also have delivered organic molecules, the chemical building blocks necessary for life. And who was constantly rearranging the trajectories of those icy objects? Jupiter. The same giant planet that may occasionally direct danger toward Earth could also have delivered the ingredients required for life itself. In a strange way, Jupiter behaves like an architect of destiny, sometimes destructive, sometimes creative, always influential. Its role becomes even more apparent when we look back to the earliest days of the solar system. Around 4.5 billion years ago, the planets we know today did not yet exist in their current form. The sun was surrounded by a swirling disk of gas, dust, and debris. Within this rotating cloud, tiny particles collided and merged. Over time, they formed larger bodies. Those bodies became planetesimals. The planetesimals became protoplanets. Eventually, planets emerged. But the process was far from orderly. Young solar systems are chaotic places. Objects collide, orbits shift, worlds migrate. And according to one of the most influential theories in planetary science, Jupiter itself may have wandered dramatically from its birthplace. This idea is known as the Grand Tack hypothesis. The name comes from sailing. A sailboat performing a tack changes direction before eventually returning along a new path. Jupiter appears to have done something similar. Shortly after forming, the giant planet may have begun migrating inward toward the sun. As it moved, its immense gravity disturbed countless smaller objects. Protoplanets were scattered. Asteroids were displaced. Entire regions of the young solar system may have been reshaped. Then something extraordinary happened. Saturn grew large enough to exert significant gravitational influence of its own. The two giant planets became locked together. Their interactions reversed Jupiter's migration. Instead of continuing inward, Jupiter turned around and began moving outward again, like a giant ship changing course, like a cosmic bulldozer sweeping through the early solar system twice. The consequences were enormous. Potential planets may have been destroyed before they fully formed. Countless asteroids were scattered. The architecture of the entire solar system changed. Some scientists believe this process helped create the stable arrangement of planets we see today. Without Jupiter's migration, Earth itself might never have formed in the way it did. The continents, the oceans, the moon, the eventual rise of life. Everything may trace part of its origin back to the movements of a giant gas world billions of years ago. The more scientists study Jupiter, the more they realize it is not merely another planet. It is one of the primary reasons the solar system looks the way it does. But Jupiter's influence extends even further, because its gravity does not only affect comets and asteroids, it shapes moons, controls radiation, dominates enormous regions of space, and perhaps most intriguingly, it may have destroyed entire worlds long before Earth ever became habitable. In fact, there is growing evidence that Jupiter may be responsible for the disappearance of planets that once existed before our own world had even finished forming. And that is where our journey goes next. When we look at the solar system today, it feels stable. 8 planets orbit the sun in predictable paths. Their motions can be calculated centuries into the future. The arrangement appears orderly, almost permanent, as if it has always existed this way. But that impression is an illusion. The solar system we see today is the survivor of a violent past. Billions of years ago, this region of space was a battlefield. Young planets collided, moons were shattered, asteroids were scattered. Entire worlds may have disappeared forever, and at the center of much of that chaos stood Jupiter. Modern computer simulations suggest that the early solar system contained far more material than exists today. There may have been additional protoplanets orbiting the Sun. Some could have been larger than Mars. Others may have rivaled Earth in size. Most are gone. The question is simple. What happened to them? One possibility is that Jupiter eliminated them. The Grand Tack hypothesis paints a dramatic picture. As Jupiter migrated inward toward the Sun, its gravity acted like a giant snowplow moving through a crowded construction site. Objects that had been peacefully forming suddenly found their orbits disturbed. Some collided with one another. Some were thrown into the Sun. Others were ejected from the solar system entirely. Imagine trying to build a house while a bulldozer repeatedly drives through the foundation. That was the environment in which the inner planets formed. And somehow, Earth survived. In fact, some scientists believe Earth's relatively modest size may be the direct result of Jupiter's migration. Without the giant planet disturbing the inner solar system, there may have been enough material for several large rocky planets to form, where Mercury, Venus, Earth, and Mars now reside. Instead, Jupiter reshaped everything. Mercury may hold some of the evidence. The smallest planet in the solar system is also one of the strangest. Despite being relatively small, Mercury possesses an enormous iron core. Roughly 2/3 of the planet's mass resides there. Compared to Earth, Mercury appears to have far too much metal and far too little rock. Why? One explanation involves a catastrophic collision. Scientists suspect that early Mercury may have been much larger. A gigantic impact could have stripped away much of its outer layers, leaving behind the dense, metallic core we observe today. If true, Mercury is not merely a small planet. It is the surviving remnant of something larger, a world that was violently altered during the solar system's youth. And Mercury is not alone. Evidence of ancient impacts appears everywhere. The moon itself likely owes its existence to one of the largest collisions in planetary history. According to the leading theory, a Mars-sized object known as Theia slammed into the young Earth around 4.5 billion years ago. The collision was apocalyptic. Millions of billions of tons of molten rock blasted into orbit. A glowing ring of debris formed around Earth. Over time, gravity pulled that material together. The moon was born. Every time we look at the night sky, we are seeing the aftermath of a planetary collision. The moon is essentially a monument to catastrophe. Without that impact, Earth would be a completely different world. Ocean tides would be weaker. The planet's rotation would differ. Climate stability might have evolved differently. Some scientists even argue that complex life benefited enormously from the moon's presence. Once again, destruction created opportunity. This pattern repeats throughout the solar system. Mars may have experienced a collision so powerful that it removed a significant portion of its northern hemisphere. The contrast between the planet's smooth northern lowlands and heavily cratered southern highlands remains one of planetary science's biggest mysteries. Some researchers believe a giant impact excavated much of the northern region billions of years ago. Even Mars's tiny moons, Phobos and Deimos, may owe their existence to debris created during that ancient disaster. Farther outward, Uranus provides perhaps the most dramatic example of all. Something enormous hit Uranus. We know this because the planet rotates on its side. Its axis is tilted by nearly 98 degrees. Imagine Earth spinning like a rolling ball rather than an upright globe. Seasons would become almost unrecognizable. Entire hemispheres would spend decades facing the sun. That is exactly what happens on Uranus. Such an extreme tilt likely required a truly colossal collision. Some models suggest the impacting object may have been several times the mass of Earth itself. The collision permanently altered the planet, and even today, billions of years later, Uranus still carries the scars. The farther astronomers look beyond our solar system, the more common these violent histories appear to be. Thousands of exoplanets have now been discovered orbiting distant stars. Many seem radically different from the worlds in our own neighborhood. Some giant planets orbit extremely close to their stars. Others follow highly eccentric paths. Some systems appear chaotic compared to the orderly arrangement we know. One particularly intriguing example involves two planets known as Kepler 107b and Kepler 107c. Both are nearly identical in size, yet one is dramatically denser than the other. Why? Scientists suspect a giant collision. One of the planets may have lost much of its outer layers during an ancient impact, leaving behind a dense iron-rich core. In other words, planetary violence may be a universal phenomenon. Worlds are not born peacefully. They fight for survival, and many lose. This realization changes how we think about Earth. Our planet often feels permanent, stable, protected. Yet, Earth's existence may be the result of countless fortunate outcomes. The right collisions, the right near misses, the right gravitational interactions. A slightly different history and our world might never have formed, or it might have become something completely unrecognizable. Perhaps the most unsettling possibility is that many of the planets destroyed during the solar system's formation may have been perfectly viable worlds, potential Earths, worlds that never received the opportunity to develop oceans, atmospheres, or life because they were shattered long before such things became possible. Some may have been consumed by Jupiter. Others may have been ejected into interstellar space, wandering forever through the darkness between stars. The solar system we inhabit is therefore not the only version that could have existed. It is simply the version that survived. And that brings us to one of the strangest discoveries in modern astronomy. Because when scientists began looking beyond our solar system, they found giant planets behaving in ways Jupiter never did. Worlds that migrated inward until they nearly touched their stars. Worlds hotter than some stars themselves. Worlds that completely rewrote our understanding of how planetary systems form. The discovery of these bizarre objects forced astronomers to rethink everything they thought they knew about planets. And it all begins with a class of worlds known as hot Jupiters. For most of human history, we only knew about one planetary system, our own. The solar system became the blueprint by which we judged every theory about planets. Small rocky worlds occupied the inner regions close to the sun. Giant gas planets lived far away in the colder, outer reaches. It seemed logical. It seemed natural. And for a long time, scientists assumed this arrangement was probably common throughout the universe. Then the discoveries began. In the mid-1990s, astronomers detected something that appeared impossible. A giant planet roughly comparable to Jupiter was orbiting extremely close to its star, far too close. The planet, known as 51 Pegasi b, completed an orbit in only about 4 days. To understand how shocking that was, imagine Jupiter abandoning its distant position beyond the asteroid belt and moving inward until it practically touched the sun. According to existing theories, such a world should not have existed. Yet there it was, and it was only the beginning. Over the following years, astronomers discovered more and more of these bizarre objects. Some were larger than Jupiter. Others were even more extreme. Many orbited so close to their parent stars that temperatures climbed to thousands of degrees. These worlds became known as hot Jupiters. The name sounds simple. The implications were revolutionary. Everything about hot Jupiters seemed wrong. Giant gas planets require enormous amounts of material to form. The regions closest to stars are generally too hot and too chaotic for that process to occur efficiently. According to traditional models, giant planets should form much farther away, yet somehow they ended up hugging their stars. The only explanation was migration. These planets had not formed where we found them. They had moved. And suddenly, Jupiter's own history began to look very different. Scientists started wondering whether planetary migration might actually be common throughout the galaxy. Perhaps planets are not born in fixed locations at all. Perhaps they wander through their systems, reshaping everything around them as they travel. The idea transformed planetary science. Today, astronomers believe many giant planets migrate during their early lives. Young stars are surrounded by enormous disks of gas and dust, known as protoplanetary disks. Within these swirling environments, newly formed planets interact with surrounding material. Those interactions create drag, and drag creates movement. A giant planet can gradually spiral inward toward its star. Some continue migrating until they become hot Jupiters. Others stop partway. A few, like our Jupiter, reverse course entirely. This is one reason the grand tack hypothesis remains so important. The discovery of hot Jupiters demonstrated that planetary migration is not merely possible. It appears to be common. The difference is that Jupiter never completed the journey. Had it done so, Earth might not exist. As Jupiter moved inward during its early history, it approached regions where rocky planets were beginning to form. If the migration had continued unchecked, the giant planet could have scattered or destroyed much of the material needed to build worlds like Earth and Venus. Instead, Saturn intervened. As Saturn grew larger, gravitational interactions between the two giants altered their trajectories. Jupiter's inward movement slowed. Eventually, it reversed. The giant planet turned around. The solar system survived. Looking back, it feels astonishingly fortunate. A slightly different sequence of events, and our planetary neighborhood could have resembled the chaotic systems astronomers observe around distant stars today. Instead of stable inner worlds, there might be nothing, or perhaps only a giant scorched planet circling close to the sun. No oceans, no continents, no life, no one asking questions about the universe. The more scientists study planetary systems beyond our own, the more unusual our solar system appears. Many systems contain giant planets far closer to their stars than Mercury is to the Sun. Others contain massive worlds moving along highly eccentric orbits that would create catastrophic instability if they existed here. Some systems seem almost hostile to the formation of life, and yet life emerged here, which raises an interesting possibility. Perhaps Jupiter's migration was not merely a dramatic event in our past. Perhaps it was one of the reasons complex life eventually became possible. By moving through the early solar system, Jupiter may have redistributed enormous quantities of material. It may have helped shape the asteroid belt. It may have influenced how water-rich bodies reached the inner planets. It may have prevented other giant planets from destabilizing Earth's orbit. In a strange way, Jupiter's chaos may have created long-term stability. The universe often works like that. Order emerges from disorder. Creation follows destruction. The same giant planet capable of redirecting extinction-level impacts toward Earth may also have helped deliver the ingredients needed for life. The same gravitational force that destroys worlds can also protect them. Nature rarely deals in simple categories. As astronomers continued searching beyond our solar system, they discovered even stranger worlds than hot Jupiters, super Earths, mini Neptunes, gas dwarfs, planets larger than Earth but smaller than Neptune, entire classes of worlds that do not exist anywhere in our solar system. Some are covered by deep global oceans. Others may possess thick atmospheres, rich in exotic gases. Many challenge our assumptions about where life could potentially emerge. And then there are the truly mysterious discoveries, signals arriving from billions of light years away, brief flashes of energy crossing unimaginable distances, phenomena so powerful and so enigmatic that scientists still cannot fully explain them. Fast radio bursts. For a fraction of a second, these events release enormous amounts of energy. The signals travel through entire galaxies before reaching Earth. Some originate billions of light years away. Their exact source remains one of modern astronomy's greatest mysteries. Neutron stars may be involved. Magnetars are strong candidates. Yet definitive answers remain elusive. Every time scientists solve one mystery, the universe presents another. That realization leads naturally to the biggest question of all. Why does Jupiter matter so much? Out of all the planets in our solar system, why does this giant world appear again and again in the story? Why does it shape asteroid belts? Why does it redirect comets? Why does it influence planetary formation? Why does it seem connected to nearly every major chapter in the history of our cosmic neighborhood? The answer lies in a simple fact. Jupiter is not merely another planet. It is the dominant force of the solar system after the Sun itself. And in our final chapter, we will explore why this giant world may ultimately be the reason Earth had enough time, enough stability, and enough protection for intelligent life to emerge at all. If you could somehow leave Earth behind and travel far above the solar system, climbing higher and higher until the planets became tiny moving dots, one fact would immediately become obvious. This is not a system of equals. The planets may seem important to us because we live on one of them, but from a gravitational perspective, there are really only two dominant players in our cosmic neighborhood: the Sun and Jupiter. Everything else is secondary. The Sun controls the solar system through its overwhelming mass. It contains almost everything. Without it, there would be no planets, no asteroids, no comets, and certainly no life. But among the worlds orbiting that star, Jupiter reigns supreme. It contains more mass than all the other planets combined. Its gravity stretches across vast regions of space. It influences asteroids, comets, moons, and even the long-term stability of planetary orbits. For billions of years, Jupiter has acted as one of the great architects of the solar system, sometimes a builder, sometimes a destroyer, always a force impossible to ignore. When astronomers reconstruct the earliest history of our planetary neighborhood, Jupiter appears again and again. It likely migrated through the young solar system. It scattered debris. It altered planetary formation. It may have helped shape the asteroid belt. It may have delivered water-rich bodies toward the inner planets. It may have redirected extinction-level impacts. It may even have swallowed entire worlds. And despite all that violence, the end result was a surprisingly stable solar system, one capable of supporting life. That stability is easy to take for granted. Every morning the sun rises. Every year Earth completes another orbit. The planets follow predictable paths. But cosmic stability is not guaranteed. When astronomers observe distant planetary systems, they often find evidence of chaos. Giant planets orbiting close to their stars, worlds moving along eccentric trajectories, systems where gravitational interactions continue reshaping planetary arrangements long after formation. Compared to many of those systems, our solar system appears remarkably orderly, and Jupiter may be one of the reasons why. The giant planet acts as a kind of gravitational anchor. Its enormous mass helps organize the architecture of the solar system. It absorbs impacts that might otherwise threaten inner worlds. It redirects countless objects. It influences the motion of bodies across billions of miles of space. Of course, Jupiter is not a perfect guardian. Sometimes it sends danger our way. The same gravity capable of protecting Earth can also redirect comets toward it. The giant planet does not choose sides. It simply follows physics. Yet, over billions of years, the balance appears to have favored stability. Enough stability for oceans to persist. Enough stability for life to evolve. Enough stability for intelligence to emerge. And perhaps that is Jupiter's greatest achievement. Not the storms, not the moons, not the colossal magnetic field, but time. Time for evolution. Time for complexity. Time for a species on a small blue planet to look upward and begin asking questions. Questions about giant storms swirling beneath alien skies. Questions about worlds that vanished billions of years ago. Questions about stars, galaxies, and the origins of existence itself. The story of Jupiter is ultimately not just the story of a planet. It is the story of influence. A world so massive that it helped shape the destiny of everything around it. Its great red spot may someday disappear. Its storms may change. Its moons may continue evolving. But Jupiter's role in the history of the solar system is already secure. Long before humans existed, Jupiter was shaping the environment that would eventually make humanity possible. And long after humanity is gone, the giant planet will likely remain there, circling the sun every 12 years, wrapped in bands of cloud, illuminated by distant sunlight, guarding its collection of moons, and continuing its endless dance through space. When we look at Jupiter through a telescope, we are not merely seeing another planet. We are seeing one of the main characters in the story of our existence, a failed star that never ignited, a gravitational giant that reshaped worlds, a cosmic architect hidden in plain sight. And perhaps the most humbling realization of all is this. Everything we have explored in this video, the storms, the collisions, the migrations, the extinctions, the mysteries, represents only a tiny fraction of what exists beyond Earth. The universe is far larger than our minds evolved to comprehend. There are trillions of planets scattered throughout the cosmos, countless storms more powerful than Jupiter's, stars larger than our sun, galaxies containing hundreds of billions of worlds, and somewhere among that incomprehensible vastness, nature is undoubtedly creating phenomena stranger than anything humanity has yet imagined. The deeper we explore, the more we realize that the universe is not only bigger than we thought. It is stranger, more dynamic, more beautiful, and far more mysterious. Every answer reveals new questions. Every discovery opens new frontiers. And every time we point our telescopes toward the sky, we are reminded that our story is still just beginning. Thank you for joining us on this journey through the storms, mysteries, and cosmic history of Jupiter and the solar system. If you enjoyed this exploration, make sure to subscribe to Epic Space News for more deep dives into the universe, the latest discoveries from astronomy, and the incredible stories hidden among the stars. Until next time, keep looking up, because out there, somewhere in the darkness, the next great cosmic mystery is waiting to be discovered.